Okay, so I want to introduce triple integrals by thinking about volume under a surface. I want to just start very simply by looking at the volume above the xy plane and below a surface. And then we can generalize a little bit, but I've got three pictures up here that that show what we're going to be doing. Now remember, uh, in Cal 1 we used single integrals to find areas between curves. And then we used double integrals later in Cal 3 to find that same area. So we're kind of doing the same thing. We can find volume under a surface with double integrals. Now remember, when we do that, we've got the delta x, the delta y, and then the function value to be the height. So we've got the area of the base times the height. Well, now we want to go to triple integrals, and we want to get the volume under a surface with a triple integral. Now, the way we do this, we think about, just imagine a surface, and then think of a region under the surface, and we're going to find the volume bounded between that region and the surface. So I've got three pictures up here. Maybe the one that's most helpful is this one right here, where you can actually see a surface, and then you see a region down here, and you see all these little stacked cubes. Okay? Now, if you think about it, so we're going to approximate the volume under this surface, and we do so by just stacking a bunch of cubes, and then getting the volume of each one of those cubes and adding it all up. Okay? So it's a little bit different way of looking at it than when we were doing double integrals, where we had the right rectangular prisms. Now we have all these little rectangles up here, or not rectangles, but little cube-looking things. And in fact, I've got one here that I took out. You know, this picture, you can see, okay, we can focus on one of those cubes. Now, and it doesn't have to be a cube. I'm going to use a cube just, for simplicity. But you notice, when we're getting the volume of this thing, we've got the delta x, which is the width. We've got the delta y, the length. And then we've got the height, the delta z. So if we want to get the volume of that little cube, what we can do is we can say delta x times delta y times delta z. And that will be the volume of that thing. Now, what I've done over here is I've kind of drawn some cubes down here where we've got, notice that if you look at this, for example, if I just look at this point right here, okay, this point right here on the corner, I could say, okay, I'm going to keep the x and the y values fixed, and I'm just going to add, I'm going to increment z. So I could say, okay, I'm going to get this cube, delta x times delta y times delta z. And then delta x times delta y times the other z. So I'll get this cube, and this cube. Then I can increment the x, or I could go this way, right? I have this x value, then this x value, then this x value, then this x value. And I'm getting all the z's up here above it, right? So in other words, we are going through systematically and getting the volume of each one of those cubes. We'll keep xy fixed and get those cubes, maybe the cubes corresponding to this corner where I have x and y fixed. I get all the volume of all the cubes up there, then I increment 1 over on the x, and then I could also increment on the y, right? So the bottom line is I'm adding up all of the volume of these cubes, the volume of each one of those cubes. Now, if we've used double summations before, we could have triple summations, right? Where we could say, okay, I'm going to do, here I've got delta z, and let's say k, delta y, j, and delta x, I. Okay? So maybe we would do this. We would say I and j and k. And what we could do is we could just go through and systematically add up all of those things, right? And if we think about it this way, just like before, if we think about a diagonal of these cubes, if we think about each cube has a diagonal, and we think about the longest diagonal going to 0. In other words, if I take the limit as the longest diagonal goes to 0, then we would say, oh, we've got an integral. This is how we're going to define a triple integral, that we would use to get volume under a surface. So what we could say is, we could say, okay, this right here, we're going to write that. The region is, we've got this region out here, and we could say this is the volume, okay? So we could say, okay, this thing we're going to write generically this way. We're going to add up all of these little volumes over this solid region. In other words, it's not really over a region on the XY plane. We're adding up all of these under this surface, right? So we've got this surface, and we're adding up all these little pieces, and we're thinking of it as a solid. Not a two-dimensional thing on the XY axis, but we're thinking of this solid region out here like this. Okay, like this one right here. Okay. So I'll use a little bit different notation. Okay, does everybody see that? Okay, now, so let's expand on that a little bit. Let's suppose, now we don't have to go from the XY plane up to Z. In other words, we don't have to have a surface and we go from the XY plane up to that surface. We could have two surfaces, and that's what this is illustrating here. You notice that I've got a surface here that's U1, and then a surface up here that's U2, and what we're getting is we're getting the volume in that surface, okay? Or we're getting the volume between these two surfaces. Okay? So here we have a picture of it, and over here we have a picture, right? So we're getting this volume right here. Now, when we think about this, and this one kind of illustrates it here. Down here we've got y equals g1 of x, y equals g2 of x. So think about this. Let's think about if we want the volume between U1 and U2. We want that volume. So we're going to have a triple integral. And we want the volume. What we're going to do is we're going to add up all these little rectangles, or all these little cubes inside here. Okay? We're going to add up all of those things. And we're going to let the diameter, the longest diameter, or the longest diagonal go to 0. Okay, so let's do this. First of all, I want to think about, well, what does the Z do? Well, if we think about getting this volume, Z goes from U1 up to U2, doesn't it? See, if U1 is this surface down here, and U2 is this one up here, we could think of Z going from U1 to U2. That's what it does. Now, after we do that, we have to think about, okay, we've determined what Z does. Now let's determine what X and Y does. So now we're looking, at this point now, we're looking down here at the XY plane. And notice they have defined for us what Y is. Y goes from G1 to G2. So let's do that. Let's just do G1 of X, G2 of X. Does everybody see that? So here's what we have. We have dz, and then it looks like we did dy. And now we have to determine what x does. Well, x, which is the last one, is going to be from A to B. Okay, so there's how we set it up. Okay. Any questions about that? No, you don't have to go in that order. You could do, you can go in any, you could arrange these however you see fit. But a lot of times what you're going to find is you're going to go Z first, and then you either go X next or Y next. But you don't have to go in that order. In fact, we're going to look at some where, you actually have to do lots of different orders. dz, dy, dx, dx, dz, dy, and so forth. Okay? Any questions about that? Okay, so let's look at an example then. Let's suppose that we've got a plane, okay? And this plane is defined to be x plus y plus z equals 6. And what we want to do is we want to get the volume bounded, well, above the xy plane and below that surface. So we want to get the volume of that region there, that solid. That's what we want. So here's the way we approach this. Now, remember with double integrals how we would have done this. With double integrals, what we would have done is we would have taken the approach of, I'm going to multiply the area times the height of all these right rectangular prisms. And if we had done this with double integrals, here's what we would have done. We would have said this is 6 minus x minus y, and then we would have set up double integrals. And we would have done this, 6 minus x minus y. We would have put that in there. And then we would have said, okay, now let's get our region. Let's see what x and y does. So down here, we've got this thing where this is like x plus y equals 6. So this right here is 6 minus x. Okay? So we could do y next. We could do y. We could say, okay, y is going from 0 to 6 minus x. And that would be, we would integrate with respect to y. And then we would say, okay, x is going from 0 to 6. And there would be our integral. And that would give us the volume. Okay? So that's something we're familiar with. Now, if we do this same, if we get the same volume, what we're going to do with triple integrals is we're not going to put anything in here. We're going to go z goes from 0 to 6 minus x minus y, like that. And we integrate with respect to z first. Now, I'm ready to integrate with respect to y, although I chose this order. It doesn't have to be this order. It's going to go from 0 to 6 minus x. Okay? And now x finally goes from 0 to 6. Now you notice that we come up with a triple integral here that gives us the same volume as this integral. But if you do the first step, if I integrate this one first, with respect to z, after the very first integration, I get this, right? I get the double integral. So you can see how they come out to be the same. Okay? Now, let's spice up the region just a little bit. Let's suppose that we want to get a volume, and let's suppose that the volume we want is bounded by this. Z equals x squared plus y squared, and z is equal to 32 minus x squared minus y squared. Let's suppose that we want the region, or we want the solid, we want the volume of the solid bounded by that thing. And I've captured a picture that I drew with Maple. Let's just go over to Maple and look at that region. Okay? So here is the region, right? And you can see the intersection here that projects down on the xy axis, or the xy plane. Okay? Now, here's what we do. Now, I'm not going to integrate this. I'm just going to set it up. First of all, we know if we're going to be using a triple integral, we're going to go from, now remember, this is a paraboloid opening up. This is a paraboloid opening down, right? It crosses the z-axis at 32, and it opens down, and it intersects. These two intersect in a circle. So the lower part of this solid is going to be x squared plus y squared. The upper part is going to be 32 minus x squared minus y squared. And I'm integrating with respect to z first. And you might think, we should use polar. Yeah, I think polar might be better. But I'm just trying to set this up and show you, and like I say, I'm not going to integrate it. Okay, now, we've gotten z taken care of. Now let's see what x and y are. So what I want to do is I have to find out, well, what is the intersection? What is the intersection of these two surfaces? And then I'll project that down on the xy plane. So let's find out what the intersection is. We've got x squared plus y squared equals, that's what z equals. Well, z is also equal to this. So I set those bad boys equal and solve, and look what I get. Really, if I go through this, I get x squared plus y squared is equal to 16. See? If I bring over the x squared, I got 2x squared, I got 2y squared, divide out the 2, and I get this. So it looks like if you look at where these two surfaces intersect and project them down on the xy plane, you get this. X squared plus y squared equals 16. So now I could say, well, I'm going to integrate with respect to y. Okay. I'll integrate with respect to y. Now, for simplicity's sake, well, let's just do this. Never mind simplicity. I was going to do, let's do the first octant. No, let's don't. Let's do the whole thing. So here I go. Y is going to go from this negative square root of, or let's do this. Let's use some symmetry here. It's going to go from 0 to the square root of 16 minus x squared. Okay? You'll see that from the circle. And then x is going to go from 0 to 4, right? Y'all see that? Any questions about that? Now, you realize what this is. This is the first octant, isn't it? Right? So if you look down here, what we've done is we've gotten that part. Well, I don't want just that part. I want all of it. So what do I need to multiply by to get this, this, and this? Yeah, so I'll multiply by 4. Any questions about that? Okay. Now, so this is just the introduction. And what we're going to do, we're going to build on this and say, well, integrals aren't all about area and volume. Integrals are about summing and infinitely many things up. So what we're going to do is we're going to say, well, what happens when you have a triple integral and you put something in the integrand other than 1? Like, let's suppose that we had some f of x, y, z in the integrand. Well, then you're not really talking about volume anymore. You've got the volume right here times something else. So we don't, once we get to that point, we stop thinking about volume so much, and we just think, okay, we've got these integrals, and we're adding up an infinitely many of these little small parts. Okay, any questions?